Dear Father, we thank you for this day. Again, Lord, thank you for the students. And just ask that you'd bless this class this morning, help us to glorify you, Lord, what we do. In your name I pray, Lord Jesus. Amen. All right, so I figured I would start out with a statement of a proposition, which should help be less confusing, because we're trying to prove the proposition last time without stating what we were trying to prove, which led to confusion. So proposition 30, or prop 30, the fixed field so my game plan today is to try to say enough about section 14.6 to try to just draw it together. So like next time we can start in 14.7. That's my goal. So I won't be able to prove everything in this section, obviously, but I want to say enough that we understand it. And we're almost there, I think. So the fixed field of the symmetric group, all right, of the symmetric group acting on the field. And this is probably something I don't emphasize enough, but the field of rational functions, right, in x1 through xn. Right? So what is the fixed field of Sn acting on the field of rational functions? It is the field of elementary symmetric functions. Now, how does Sn act on the field of rational functions? It acts basically by permuting the indices of the x's, right? So what's the proof here? How do we start? Let's see here. Now, I guess this should remind us which we built how did we do this? We built the S1, S2, Sn from what? From x1? Is that right? And in particular, we looked at what? We looked at x1, or x minus x1, right? X minus x2, x minus xn, right? This generic polynomial, and we saw that that was equal to x to the n. What was minus, right? Minus s1, x to the n minus 1, da-da-da, all the way down to plus minus 1 to the n, the nth symmetric, little sn, right? So the point is, let's see here, what's the point? Thus, f with the with the roots x1 through xn adjoined is splitting field for what? Hence, the degree of the extension of f adjoined the x's, right, over the f adjoined the elementary symmetric functions is at most what? N factorial, right? Yeah, by our basic just extend. Quotient theorem. And but on the other hand, so great. But what about what about Sn? How does Sn play into this story? But if sigma is an element of Sn, which is embedded where? Embedded in what? F, the f x1 through xn, right? In other words, look at the copy of Sn, which is naturally found inside the automorphisms of f adjoin these n generic roots. Then what can we say about, sigma of the jth elementary function? It's equal to Sj again, right? In fact, I think you probably could use that as a defining. Well, it's not quite right. I mean, it's tempting to define elementary symmetric functions as the functions which are like this. That's not quite right, because we need different. We really do want them to break up by degree, like the linear, the quadratic, the cubic, and so forth. So there's more to it than that. But this is certainly a feature of them, which is important.
Yeah, the symmetric functions are the ones that are like this, but the elementary symmetric functions are special.
So you say the S's are the elementary symmetric functions?
Right.
Thank you. That word was missing from my mind. And you're right, we do use the term symmetric function in a more generic sense soon. So joining the word elementary is helpful. Thank you. Now, so anyway, the point is that they fix Sj, right? And so what's that mean? Yeah, what's it take to be in the fixed field of Sn? You fix all the adjoined elements.
Because we know Sn, we know the embedding of Sn fixes F.
So we need that sigma of k is equal to k for all k in F adjoin the elementary symmetric functions, yeah? And if we know that this is true, then it's clear that it fixes all of the generators over S, the adjoined elements, as you're saying, and hence it's in the fixed field. So right. So apparently the embedded symmetric group is a subgroup, right, of the group of automorphisms which fix the. I mean, it's a subgroup of. I'm trying to say is this has subgroup the stink. Still not right. This I guess got to write more. So thus, if we look at the automorphisms of Fn x1 through xn, which fix the elementary symmetric functions, right? It contains what? Copy of Sn up isomorphism. But we know it's a Galois extension because it's the splitting field, right? Which means the degree of the extension has to match the degree of the group of base field fixing automorphisms. But that set of base field fixing automorphisms is at least n factorial big because it's got a copy of Sn in it. But on the other hand, it can be at most n factorial big because of our initial observation up there. Consequently, it follows that the degree of this extension is in fact equal to n factorial. Right. So this implies. And what does that say then? So there There you go. The fixed field of Sn acting on the field f adjoining the generic roots x1 through xn is the fixed field of the elementary symmetric functions built from those roots, right? To be more, these are built from the generic roots, right? All right, so that brings us to definition. A rational function f of x1, x2, xn, right, is called symmetric if what? Unchanged by any permutation of its inputs, right? See, I should make this class a prerequisite for advanced calculus. That would help me out here. Because we run into this same kind of combinatorial stuff when we're building completely symmetric or completely antisymmetric tensors, right? Same. You think that would reduce the class size of advanced calculus, yeah? Reduce it to 0? Yeah, you're probably right. Corollary 31. This is the fundamental theorem on symmetric functions. Any symmetric function in variables x1 through xn, all right, is a rational function, all right, in the elementary symmetric functions. Yeah. Proof. A symmetric function lies in the fixed field of Sn. Hence, it is a rational function in S1 through Sn. Funny. And he says, okay, so if we have a polynomial in x1 through xn, which is symmetric, then it's actually going to be seen to be a polynomial in the symmetric functions. This is kind of neat. These examples are cool. So, okay, so what's he saying? He's saying that you can always rewrite a polynomial which is symmetric, a multivariate polynomial, right? Which is symmetric in the inputs. You can rewrite it as a polynomial in the symmetric functions built from said inputs. So like his example, if we look at x1 minus x2. So I mean, all the examples are not for rational functions; they're actually for polynomials. But you know, whatever.
Does he prove if he limits polynomials, then he can limit what they're built from?
Well, it's just basic degree counting stuff that it's going to be polynomials, right? Because if you start with a polynomial in x1 and x2, for example, squared, it has to be a quadratic polynomial in x1 and x2. But if you look at how the elementary symmetric functions are built, they have the same degree as what they're built from, you know? I mean, in the sense that S1 is first degree. S2 is built from quadratic. It's built from, you know, things, homogeneous things of degree 2 and the variables that.
Yeah.
But
I guess that just doesn't entirely convince me that we therefore always have a weighting for polynomials without needing inverses of the S's. But maybe I need to read over it.
maybe, but these examples will illustrate it. So.
Right, but does he give an explicit algorithm, or is it just, are these just examples? Oh no, he says he outlines it in
Yeah. The proof of this fact is implicit in the algorithm outlined in the exercises for writing a symmetric polynomial as a polynomial in the elementary symmetric functions. So,
yeah. Okay.
if you would, now, suppose that some of the finite field, no, I shouldn't offer you this. I might need your solution. Never mind. I was about to say you could trade one of the problems that's based on like finite field extensions for that exercise in this section if you wanted. I still offer that to you. If you'd like to like give up on some other problem to do the problems in this section on executing that algorithm, if you're interested in it, feel free to trade one of the problems I've assigned for the problem you're interested in this section. Okay. And generically speaking, guys, this is kind of the sort of thing that's always possible in here. If you ask me, there's a certain amount of haggling which is allowed. Don't usually allow haggling in courses; it would lead to chaos. But there's a limited number of you in here, so.
Oh, here you go. 37 to 43.
37 to 43. 37 to 43.
That's a lot.
Huh. Cool. Okay, so just enough so you understand what I just said. x1 minus x2 squared is equal to x1 plus x2 squared, right? Minus 4 times x1, x2, but that's what? That's s1 squared, right? Minus 4s2. So we start with a symmetric polynomial in x1 and x2, and in the end, we've got a polynomial in the symmetric functions, right? Or here's his, actually, he has 2 other examples which you guys can look at, which are cool. But maybe it'd be fun to try to, remember, so you guys have seen me talk, most of you I think have seen me talk about my calculus over an algebra. And one of the things I'm fond of looking at is the 3 hyperbolic numbers, which are basically generated by j, where j cubed is equal to 1. So a typical 3 hyperbolic number looks like something like zeta is x plus jy plus j squared z. And a typical fundamental representation, the matrix representation of that, 3 hyperbolic number. It's a 3 by 3 matrix. It has the form x, y, z. X is down the diagonal, and then the y and the z kind of flows over the top. So then that goes, the y kind of flows up to the top, and then the z flows down like that. This is the regular representation of a 3 hyperbolic number, right? The determinant of this right, is equal to x cubed plus y cubed plus z cubed minus 3 times xyz. This is a symmetric function in xyz. So according to this theorem, I can rewrite this as a polynomial in the symmetric functions built on x, y, and z. Thinking of x as x1, y as y2, y as x2, and z as x3. So, do you remember, King?
X plus y plus z.
X plus y plus z, yeah.
You want to write the next factor into symmetric or just say the normal one?
Yeah, okay, yeah, then, okay, fair enough. And then what is it, minus?
Minus xy minus x. Minus yz minus xz.
Let's see here. So this, maybe I should write up here. This is what? S1. Is this anything? I can change that into, this is x plus y plus z squared, you said? Minus what? Twice this thing? So this is actually s1 squared minus 2s2. Oh, so I need a 3s2 there? King, you have spent too much time messing with these. You have an unhealthy understanding of them.
I mean, it's still very mysterious to me how to factor the full hyperbola.
Oh, so I've reached the limits of your technology. King is working on like finding the submultiplicative constant over the algebra, so he spent many, many hours fussing with these things. This is why he knows this.
I've just fussed with partially, not
Yeah.
really.
But anyway, if we believe King's algebra, which I've not checked, right? But I think it's reasonable. If we square this, certainly we get the x squared, the y squared, the z squared, and we get cross terms, right? And it seems like we'll get 3 of each variety. You just do counting. 3 times 3 is 9. There's 9 terms, right? So 3 of them are here. There's 6 in the cross terms. The 6 cross terms give us the 6 terms, which would be in here. I think 6 terms? Wait a minute. Oh, but okay, so this would be 9 terms, but you're right. Okay. Anyway, there you go. So it's kind of neat. Anyway, so getting to the point here, theorem. Theorem 32. Here's the punchline that I've told you guys before, basically, but the general polynomial x to the n minus s1 x to the n minus 1 plus s2 x to the n minus 2 plus minus 1 to the n Sn over the field of elementary symmetric functions is separable with Galois group Sn. And so essentially this just uses everything we've built so far, right? There is some thing he rules out logically in the paragraph before. There's some nuance I'm skipping over, but you know. So he says, this result says that there are no relations among the coefficients of a polynomial of degree n. Excuse me, this result says if there are no relations among the coefficients of a polynomial of degree n. That's what we mean when we say that the SI are indeterminates. So to say SI are indeterminates, I think this is kind of an important point. In the x1, x2, xn. This means what? There do not exist relations between the indeterminates, right? That's not quite accurate.
Yeah, what exactly does that mean?
Interesting. Relations
It's like,
amongst the S1.
it's like say that I have a field and then I pick out 2 things.
Still not right. Yeah.
Don't they have a relation between them and then when it's
They have to commute, right? I mean, indeterminates, we think of commuting indeterminates, right? So you pick indeterminate Pac-Man, indeterminate Ghost, Ghost Pac-Man's Pac-Man Ghost. I mean, that's the world we're living in.
right, but I thought that that the idea of this is that these indeterminates are used to model like kind of a general case of actual elements of the field.
Mm-hmm.
So like, I don't know, what is it like? Because anytime I have 2 elements of the field.
So you're saying indeterminates are just variables.
Well, no, I'm just saying like anytime I have 2 elements of the field, I can take one and multiply it by its inverse times the other one. And that gives me
Oh, I don't think so. I don't think we talk about the inverse of indeterminate.
But they're rational functions.
Right, except in the context of looking at the rational functions in the determinants.
Okay, so
It depends on the context.
what exactly
Exactly. That's the question. Let me read the sentence again carefully. This result says if there are no relations among the coefficients of the polynomial of degree n, which is what we mean when we say SI are indeterminates above.
Right. Or what does it mean that there are no relations? Like what exactly does it mean by a relation? It's probably something we covered in linear that I've just forgotten.
I don't know. I mean, he uses the same kind of argument in the paragraph above, which I was trying not to get into. So let me read through that paragraph. He says if we define the roots of this polynomial to be x1 through xn, the SI are precisely the elementary symmetric functions of the roots x1 through xn. Right? Moreover, these roots are indeterminates as well in the sense that there are no polynomial relations over f between them. Okay? So he's talking about polynomial relations. He says, suppose that we have p of t1 through tn, a non-zero polynomial, and n variables with coefficients such that when we plug in the generic roots, we get 0. He says, then the product p tilde over all of the permutations in Sn gives us a non-zero symmetric polynomial, and this gives us a non-zero polynomial relation over f among the S1 through Sn, which is a contradiction.
So does he mean like if we have a field F and then we have elements S1 through Sn that are not in F, then a relation between them would be a polynomial with coefficients in F where the variables are in?
I don't know. I have to read this more carefully. I mean, maybe this is helpful. This is not always possible, he says, right? He says that what we're doing right now essentially makes sense over the rationals, but it doesn't quite make sense over a finite field, because we have proved previously, or skipped over previously, that the finite field have a cyclic Galois group, right? So in that sense, generic polynomials do not exist for finite fields, because we can't create a generic polynomial over a finite field which has a full symmetric group as its Galois group. So you can't keep the structure of a finite field and have indeterminates. The finite field comes with baggage, I would think was what you're saying, Sam.
Well, I mean, maybe that's an implication of what I'm saying. I just wanted to understand exactly what he means by
What precisely is
relation.
what precisely is an indeterminate?
Well, no, I know what an indeterminate is.
Oh, okay.
What he means by it when he says the word relations.
He seems to be saying a polynomial in the indeterminate such that when we plug in the roots, we get 0. That's what I mean, that seems to be the genesis for his contradiction in the paragraph before. Like he says, suppose you have a non-zero polynomial. Let's see here. Blah, 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 blah. He says, suppose you have p of t1 through tn, a polynomial in the n variables with coefficients in f such that when we plug in x1 through xn, we get 0.
So what's the difference between such a polynomial and this one right here? Isn't this polynomial exactly one that has x1 through xn roots? Or am I misunderstanding?
Yeah, the polynomial in the t is a polynomial in the p of t1 through, he says p of t1 tn equal to 0, and here this guy is coefficients, not coefficients in f, not in I've got it written somewhere here. Not in this thing. So I guess you can write such a polynomial relation in a finite field. I mean, I don't know. No? Not true either? I don't know. But
I mean, we prove this for even finite.
yeah, well, parts of this are true for finite field. What's not true for finite field? I mean, something breaks down because the finite field has to have a cyclic Galois group. I mean, a polynomial over a finite field has a cyclic Galois group.
I guess that's what finite subgroup of a multiplicative finite subgroup of a multiplicative group of field is cyclic. I never heard of cyclic. I never heard polynomial over finite field.
Let's see here. I'll find it here for a second. It is the section that I haven't gone over entirely. Well, the Galois group of maybe it could be a specific kind of finite field. I guess maybe. I mean, theorem 26 says that the Galois group of the cyclotomic field by Q adjoining the nth roots of unity is isomorphic to the multi-group of units of Z mod NZ.
I mean, that's for specific polynomial.
Right.
But like the step 4.8.
Oh, right. I need for generic. Yeah.
Are we talking about the step in 14.3?
14.5 most likely. Maybe not. Nah. No, that's not. Maybe 14. Maybe you're right, Sam. Maybe it's 14.3.
Because like, are you saying that are you talking about the idea of are finite fields besides the specific ones?
I'm sorry?
Are you talking about the idea of finite fields besides the specific ones described in 14.3, or are you talking about?
I believe the ones described in 14.3 most likely.
Yeah, because I thought those are all finite fields.
Right. Finite fields have to have the form what? F mod P or F mod P to the n, right? Them's your choices. And I think section 14.3, goodness gracious, trying to find the punchline here. Not so easily found. Let's see here. Any finite field is isomorphic to F mod P to the n for some prime P. It is the splitting field over Fp for the polynomial x to the p to the n minus x with cyclic Galois group of order n generated by the Frobenius automorphism sigma p. And the subfields of Fp to the n are all Galois over Fp and are one-to-one correspondence with the divisors d of n. They are the fields Fp to the d, the fixed fields of the dth power of the Frobenius automorphism. So, let's see here. So, I mean, he's saying that forbids this construction in a finite field. And then he goes on to describe what does this construction do for us, for different orders, right? So to understand that, we have to build this thing called the discriminant. All right. So he says the notion of generic polynomial. Sorry. First a second here. He says over the rationals, one can make precise that the notion of generic polynomial. We can make precise this notion of generic polynomial, and it's true that most polynomials have the full symmetric group as the Galois group. I mean, we've seen that we've seen that realized for the Q adjoin what? For x cubed minus, I keep going back to this, but it's the good example, x cubed minus 2, right? The Galois group of that was S3. But of course, that it has not happened in every case, but it can happen is the point. And what he just claimed, what I just read, is that it happens more often than not. Right? It happens more often than not. Now, how exactly you say something happens more often than not in an infinite set of rational functions, I'm not sure. That seems... Yeah, I think that seems like a job for someone who cares more about probability than I do at the moment, which is, my bad. Let's see here. So definition. This is actually an important idea beyond our current discussion, I think. But the discriminant So you guys are familiar with this notion as it attaches to what? I can't spell. Discriminant. D of x1, x2, xn. All right. D is equal to the product I less than n of xi minus xj squared. He says, define the discriminant of a polynomial to be the discriminant of the roots of the polynomial. So the discriminant of f of x and f of x, right, is the discriminant of the roots.
Should be I less than j, right?
Yes. Good grief. Oh no. That's not good. That's not a good sign. It's okay. I'm just doing a test review. So joke's on them. He says, okay, so for n, now here's an interesting factoid you may not be aware of. For n greater than or equal to 5, there's only one normal subgroup of Sn.
Is this going to be the key in the arithmetic formula?
It's definitely an ingredient in the discussion. So for n greater than or equal to 5, there is only one normal subgroup. What is it? What's the only normal subgroup of Sn? Yeah, An. An is a normal subgroup of Sn because it has index 2 among other things, right? And well, that's for n greater than or equal to 5. I mean, there are other normal subgroups for S4 or S3 or S2. Well, maybe not S2, but hence, here's the point. In general, there's only one normal subfield of f adjoining x1 through xn, which contains f adjoining the elementary symmetric functions, s1 through sn, and it's an extension of degree 2. So implies that there is only one normal subfield Oh, I forget the technical meaning of that. We talked about normal extensions, yeah? Separable normal. That's the sense that normal is being used there. Containing, he calls it K. All right, anyway, let me get to the point here. He says, we actually first defined the alternating group and saw that a permutation in the symmetric group and is an element of the subgroup AN if and only if it fixes the product. See here, he points out that this is an, I mean, I'm not sure where this adds to the discussion, but this is a polynomial over the integers adjoined x1 through xn, all right? He says, it follows by the fundamental theorem that if f has characteristic from 2, then the square root of d generates the fixed field of AN. Square root of d generates fixed field of AN, right? And generates a quadratic extension of what? of K, the field adjoining the elementary symmetric functions. That gives us proposition 33. If the characteristic's not 2, a permutation in Sn is an element of An if and only if it fixes the square root of the determinant. Discriminant, rather. So sorry. He says, we now consider Galois groups of separable polynomials of smaller degree, less than or equal to 4 over a field. And we'll assume the characteristic is different than 2 or 3. And let's see here. He says the discriminant is symmetric in the roots of f of x. Hence, it's fixed by all the automorphisms of the Galois group of f of x over the elementary symmetric functions. And it follows by the fundamental theorem that D is an element of f. The discriminant can, in general, be written as a polynomial in the coefficients of f of x, which are fairly complicated for larger degrees, but we give specific formulas for degree 2 and 3 and 4. Proposition 34 says the Galois group of f of x is a subgroup of An if and only if the discriminant is the square of an element of f. Again, the Galois group is a subgroup of An if and only if the discriminant D is a square of an element of f, the field. Let's see here. So let me just write down degree 2. Degree 2 should be familiar to you guys. So D is S1 squared minus 4S2. Does that make sense? I guess we probably could write it down. More generically, it's what? X1 minus X2. Oh, that was the point. That was the point of that example earlier, wasn't it? Yeah, okay. That was not so... So this is, again, yeah, this is S1 squared minus 4S2. All right. Which, let's see here. So we're looking at x squared plus, and, you know, I almost kind of want to rewrite this as bx plus a just to make it more familiar. But, I mean, well, usually, oh, you're right, bx plus c. Okay, so there's no hope. All right. Now, why is it, he says that this is equal to minus a squared minus 4 times b, which is a squared minus 4b, yeah? I think that goes back to the calculation I put on the board last time in terms of lambda 1 and lambda 2, where there we saw explicitly the relation between the roots and the elementary symmetric functions, right? Or I guess you could just, you know, well, between the coefficients, right? We multiply out x minus lambda 1, x minus lambda 2. We saw that the coefficient of the b was essentially the determinant, which was the product of the roots, and the coefficient in the middle term was the trace, which was the sum of the roots in the second order case. So it's just that. But of course, that is the discriminant that we know. And so his point is the polynomial is separable if and only if what? A squared minus 4b is not equal to 0. In that case, the Galois group is a subgroup of S2, cyclic group of order 2. So what? So it's basically Z2, right? Z2 is the Galois group of a quadratic. Unless what? Unless the discriminant is in fact 0, right? Well, I guess it doesn't. Yeah, if the discriminant's 0, then we can rewrite the quadratic as the square, right? It's reducible, and then it follows that well, what can we say here? Actually, a squared minus 4b is a rational square, he says, which completely determines the possible Galois groups. Let's see here. And then he says, well, this just restates what we already learned about quadratic extensions, right? So, polynomials of degree 3, a little bit more complicated. Whew. So, got to play some games with mind your P's and Q's. And after a little bit, he finds the discriminant is minus 4p cubed minus 27q squared. That is, in fact, a... The depressed polynomial's got to come into play here somewhere. I mean, his 14.16, he starts with a cubic rather, which has quadratic order. Then he makes a substitution which depresses the polynomial to g of y. Depressed polynomial is one which doesn't have its next to leading order. Depressing the polynomial is the generalization of completing the square. This is a trick you can always play. And by depressing the polynomial, then he gets access to the rather sophisticated, I mean, not obvious formulas between p and q, discovered by those Italians in yesterday. How many more minutes do I not have? -2? Okay. So that leads us to looking at the Galois group of a cubic, and then he also has, tell you what, I will try to run through these things next time, and then we'll go into, I mean, I'm not going to work them out. I will state them, you know. You could spend a week of lectures, I think, really doing the cubic formula justice, right? I mean,
Working out,
yeah.
Working out is like pretty straightforward in the book, but like if you'd be able to go over the part where he's like, okay, given this working out, here's what the possibilities are for the Galois group.
Yeah, that's the part I want to try to focus on. Yeah, yeah.
Because like that pulls together a bunch of different results that I didn't remember all of them in my mind.
I will do my level best to explain that Friday. Of course, Wednesday. What can I say about Wednesday? Yeah. Day for studying and catching up on homework. Woo! Right? Yes. Okay. Oh, so you guys have your